Okay, let's finish up series motor speed control by working this example 5.5. And what I thought I might do before we do that is introduce you to the librarian here at my place. And here she is. This is my constant companion through the pandemic, and she never misses a video. This is Saki. Saki was a stray. I never had a cat ever. Never wanted a cat, but I took Saki over and made me a cat fan. But anyway, so section 5.5 or example 5-5 is going to utilize this characteristic curve of the series motor. And I really like this problem and want you to make sure that you understand it. It's going to be like this application of this per unit thing that really helps to show you the benefits of that. And, you know, I know when we initially were studying that way back in chapter 1, you know, I told you that you know, it may not be immediately clear as to why we're going to the trouble to do this, but this is the type of problem where you really start to see the usefulness of it. Okay, so let me switch over to that. So this problem says that we have a 15 horsepower, 240 volt, 1780 RPM DC series motor, and it has a full load rated current, or sometimes we'll just see that abbreviated as FLA, full load current, of 54 amps. Its operating characteristics are given by the per unit curves of figure 511. Well, these per unit curves that are per unit curves that are grafted here together represent all DC series motors. So nowhere on this characteristic curve do we see anything that shows us the characteristics of this particular example. It doesn't say anything about 15 horsepower or 240 volts or 1780 RPMs or FLA, full load current of 54 amps, but we can apply this curve to this particular example if we use base units, okay? So what we want to do is what's given to us is going to be our base, or our bases in this case. So we're given that it's 15 horsepower. Now, if we looked on the motor nameplate and it said 15 horsepower, that would indicate the amount of power that's available at the motor shaft to do work, okay? It's not the total power input, it's the power available at the output side. It's telling us that it's 240 volts, that it's rated to run at 1780 RPMs, and it has an FLA of 54 amps. Now, those are what we call, those are our base units. This is nameplate information, okay? And that's what we use, you know, to determine what our bases are. And from these bases, we can construct other bases. He's asking us two questions. First, what is the speed and current when the load torque is 24 Newton meters, and what's the efficiency under those conditions? Now, to begin a problem like this, we need to establish a base power, a base speed, and a base current of the motor. And if you flip over to page 106, you know, this is done for us. First off, what we need to do here with this 15 horsepower, we need to turn this into watts. So the 15 horsepower, 1 horsepower, 746 watts, right? And that would give us 11,190 watts, okay? So that's our base power, or we could just call that P sub B. Right. Our base speed is what's given here, and our base current is what's given here. Okay, so let me pause that, clean this up a little bit, and we'll finish this thing. Okay, so I'll clean this up a little bit so we can see these bases that were given to us. No calculation involved, right? Just recognizing that nameplate information gives us bases. So what we can do from these bases that we have, we can calculate the base torque, and torque is 9.55 times the power divided by the speed, and plugging and chugging, plugging our bases in from over here and calculating, we come up with the base torque is 60 Newton meters. Okay, now, what we need to do now at this point is we have a base torque, and we need to take the information given to us in the problem where it says, initially, how was it worded? It says, what's the current and speed when the load torque is 24 Newton meters? Okay, so we want to determine the current and the speed, and we have a curve here from the characteristic curves that are going to allow us to do that. So if you remember, like if 60 Newton meters is the base, okay, and we're dealing with 24 as a particular, this is our base, right? And so, you just do the division, 24 divided by 60, and I get 0.4 per unit. Okay, so going to our curve, okay, we'll think about these as, okay, this would be 0.2, 0.4, 0.6, 0.8, and 1, 0.2, 0.4, 0.6, 0.8, and 1. Now, so we can use this 0.4 per units and use the characteristic curves and make the determination that we need to make. Otherwise, we could also do this through some mathematical manipulations, but the curves are in so much easier to use the curves than to make this just a mathematical thing. We visualize it too, which I think is neat. Okay, so I modified our curve a little bit so we could see these values. So looking at the correct curve, excuse me, a torque of 0.4, a torque of 0.4 per unit is right here. And let's use a different color here. So I'm going to come out here. I'm looking across here, 0.4 per unit. And so the 0.4, and let's say we want to know the speed at that point. Well, if I follow this out and where it intersects the torque versus speed, I see it at 1.4 per unit. So I write down 1.4, and the base speed was 1780. 1.4 times 1780 tells me that my speed at that point would be 2,492 RPMs. Okay, so it's going to be running above rated speed. And so the second thing it asked me to find would be the current. And the current at that point is 0.6 per unit. All right, so I've got 0.6 per unit. I have a base of 54 amps. 0.6 times 54 gives me 32.4 amps drawn at that particular point. Okay, so really neat applications for this DC series motor, looking at things at different points. And you might say, what's the usefulness of this? And the usefulness of this is that it allows us to explore conditions for different applications that we might place this DC motor in. And maybe we're having some issues or something with the motor. And so, exploring the conditions that surround that may cause us to change some of the areas or levels that we might operate the motor. Okay, so anyway, just trying to make this a little bit real. And then the last thing he says, let's calculate the efficiency. So efficiency, we have an equation for that, the efficiency, and this is for, really any system is the input divided into the output. And so the power in this particular case and the power out, we're going to use two different equations. The power in for this situation that we were just operating in, I had the voltage, which was given at 240 volts. That's not going to change. But the current was 32.4 amps. So the power in was 7,776 watts. Power is current times voltage. The power out, we're going to use our power of a motor formula, which is the speed times the torque divided by 9.55. Again, always have these equations available to use, but I love for you to have this idea about this direct relationship between speed times torque and all that in terms of the output power. But anyway, so this is for our situation. We found it to be 2492, and the torque was I forgot, it was 24 Newton meters, and then that divided by 9.55. And so that comes up to be 6,263 watts. So I put this in and I got this out. And so the efficiency of that is going to be 6263 divided by 7776, or approximately 0.805, or 80.5%. Now, that's not a bad efficiency. Electric motors are designed to operate at higher efficiencies than that. Some of the efficiencies get up into the mid and even in large machines, upper 90s, but still 80.5% is not too bad in terms of the energy in that's converted to output. And so that gives us that value. At the same time, we might say, well, for efficiency's sake, this might not be where we want to operate this motor, most of the time. Maybe there are conditions where it would be a much higher efficiency, and I'll just go ahead and tell you that point is always going to be right here. And motors, generators, they're all designed to operate at a certain maximum efficiency. And, those are given at these 1 per unit. At the rated load, they're designed to be most efficient at these points in terms of their operation. Okay, so that's 5.9.